let me introduce our speaker today. It's on behalf of the entire of the Mercury Lab. I want with a great pleasure to welcome Professor André Martins to our webinar series. Thank you very much for accepting our invitation. I have a few things to say about Professor Martins. We'll start with the classic. He obtained his PhD in 2012 from CMU and also IST Lisbon. And then I'll move on to other things that some of which I had witnessed when I was a PhD student myself. That ever since Professor Martins leads an ever-growing group of researchers there at the IST Lisbon, with numerous important things to show for, an ERC, deep spin, which a good portion of it I think we're going to hear about in today's talk. Various best paper awards, and at the same time on the side, Professor Martins has started a number of industrial research labs in Portugal. He's also the VP of AI research at MMLL, and if you're interested in machine translation, I'm sure you know about MMLL. And he also gave us the amazing Lisbon Machine Learning Summer School, which this year is actually its 12th anniversary. I believe it's the 12th edition. And it's happening in July in sunny Lisbon, as always. I myself learned a whole bunch from Professor Martins' research. I think it all started for me at his PhD thesis, which really is quite a book, quite an amazing book. I then learned from a number of other opportunities from his 2014 MMLL tutorial on linear programming decoders, and after that, his ACL 19 tutorial on structure prediction. And I think pretty much from every one of his papers, really. So Professor Martins has made substantial contributions to structure prediction from linear to deep models. And I'm very excited that he has joined us today to tell us all about his research agenda. So with no further ado, André, the floor is yours.
All right. Thank you very much for the very nice introduction. So it's a great pleasure to be here. So the work that I'm going to present today, it's all work done by my students in the Sardines group. We just rebaptized our group Sardine. It stands for Structure-Aware Modeling for Natural Language. The acronym is a little bit, it's not very direct, but it's Sardine is something that is very related to Lisbon. Yeah, so here's another picture of Sardines art at work. So most of the work that I'm going to describe has been developed in the Deep Spin project. This is a ERC, which is almost finishing. There's one more year to go, where the main goal is to put together deep learning and structure prediction to tackle problems in natural language processing, with a bit focus on machine translation, generation, and quality estimation in general. All right, so here's a quick gist of what I'm going to talk about today. So, those of you who are around for some time, you might remember that back in the 2000s, feature selection was a big thing. Sparse modeling was a big thing. It was mostly used before neural networks became so popular again with linear models, and the goal was mostly to use some kind of sparse regularization, for example, using the L1 norm, in order to assign 0 weights to some features. And by doing that, we are able to select features that are relevant and discard the ones that are irrelevant for more model. And there's plenty of extensions that put some structure on top of that, with things like the group lasso, fused lasso, and many other models. So here I'm going to talk a little bit about how to go from there, from sparse modeling, to something that I'm calling here sparse communication, which I'm going to argue that it bears a lot of similarities with sparse modeling in many different ways, but as a little bit of a different flavor. Okay, so this is something that we use usually with neural networks, and with most work being done after 2015. And the main idea is to try to model neural activations that are sparse. Okay, and there's plenty of reasons why we think that sparse neuron activations are a good idea. There's been some arguments invoking biological plausibility. I want to get into that territory. But the idea here is that you might have a very complex neural network, but where the predictions are triggered only by a very small circuit inside the neural network. Okay, only a few neurons, depending on the input, are going to get activated and being responsible for some prediction. And we see this kind of sparse activations happening in different scenarios. For example, with rectified linear units, these activations are able to shut down some neurons completely. When we do regularization with dropouts, stochastically, we're also dropping some neurons. And in this talk, I'm going to talk more about sparse attention mechanisms, which is something that my group have been developing across the years, which also falls into this category. So basically, today I'm going to talk a little bit about several transformations that can capture both sparsity and structure. And they all have in common a bunch of different properties. So all of these transformations are end-to-end differentiable. This means that we can still run our gradient backpropagation algorithm to learn the neural network weights when these transformations are present. We can use them either as a hidden layer, for example, if you use them in an attention mechanism, or we can also use them as output layers, as a loss function. And I'm going to argue, and this is maybe the most recent work that I'm going to present today, we are going to argue that this can be useful to make a bridge between the continuous and discrete worlds. I'm going to be a little bit more precise in a bit. All these transformations have been quite effective in several NLP tasks. So the building block for today is really, I don't know if you see my mouse. Can you see my mouse? You do, okay, perfect.
Yes,
so the building block is basically how can we map from a vector in a Euclidean space. Here we have a vector Z. The components of Z can be positive, negative, there are not constraints. But what we want to do is to map this vector into a probability vector, which is a point that lives in the probability simplex. Okay, so basically a vector with the same dimensionality as Z, but where all the components sum to 1 and they are all non-negative. Okay, so we're going to talk about different ways of achieving this kind of transformations. So here's a little bit more about this relation between discrete and continuous. The traditional setting in many scenarios, not just machine learning and NLP, is that you typically opt by choosing to use discrete or continuous random variables, and this is a choice that you need to make. And and sometimes this choice is not easy. So, for example, if you want to do something that has something to do with language, if you want to use text as a latent variable in our model, for example, language is symbolic and discrete, and this contrasts with the way neural networks work internally, where they use and they learn continuous representation. So it's there's a big debate about how we can reconcile these two worlds. I think that we should really look at what can happen in between these two dimensions, discrete and continuous. And I think that sparsity can be one possible way to try to bridge this gap. But there is a problem, which is, the theory is not ready for that yet. So there's if you look at many textbooks in probability theory and graphical models and so on, they often exclude things that are sparse because they can complicate things a little bit. So, for example, if you are doing work in graphical models, typically we exclude probability distributions that assign 0 probabilities to some events, just because it makes things easier and it makes the connection between graphs and the conditional independence easier to establish. There's also other instances like the Pitman-Koopman-Darmon theorem that relates exponential families with the minimal sufficient statistics. It also excludes from the equation things where the support of the distribution can vary. And finally, maybe the most obvious example is that if you have something that outputs a sparse probability distribution, something that can assign 0 probability to some events, if we miss the correct event, if we assign 0 probability to an event that occurs, we're going to end up with the log likelihood of minus infinity. So we cannot learn with the usual maximum likelihood estimation strategies. Okay, so here's a like a very short motivation about what do you mean when we say that we are trying to put discrete and continuous things together. Let's suppose that we have this character called John that needs to split his time between work and home. So he works 8 hours per day, stays home 16 hours. So you can represent John's location with a very simple PMF, probability mass function that looks like this, with 66% probability is at home, with 33% probability is at work. But in practice, it's not like that because John needs to go from one side to the other, right? So it's sometimes in transit between work and home. So if you want to model John's location, taking that into account, then we are starting to see something which is a little bit of a hybrid between continuous and discrete, right? So at any particular time, John could be in his way from home to work or vice versa. So he's going to be walking. This is represented as a continuous random variable. So it's going to be with 0 probability in any particular point inside this line. But on the other hand, we are going to have these point masses both at home and work, because it's going to, once he arrives to one of these places, it's going to stay there. And so with some finite probability, is going to be in that exact point. Okay, so we can represent that as a density with some Dirac deltas associated with these two locations. If we are just working in these 2 dimensions, we might do well. We might be fine with this, but things are going to become a little bit trickier as we move to higher dimensions, and this is something that I'm going to show in the last part of the talk. All right, so the question here is John's location discrete or continuous? And I think it's mixed. Okay, so we're going to talk a little bit about mixed random variables to address these kind of things. Okay, so let me get started with transformations. So going back to the point of how can we map a point in the Euclidean space, a point Z, onto a probability vector. So the typical way of doing this is to apply the softmax transformation, which I'm pretty sure everyone here is familiar with. It's very simple. We just take each component of our vector Z, we exponentiate it, and by exponentiating, we guarantee that it's never going to be negative, and then we normalize it, right? So by construction, this is going to lead to something which is a valid probability vector. It sums to 1 because you are normalizing, and it's going to be non-negative because you are exponentiating it. Actually, it's a little bit stricter than what we might want, okay? So because the exponential function is strictly positive, then this is also going to give us a dense probability vector. We are never going to have a probability of 0 to any event. It can be arbitrarily small if the corresponding component of Z is very negative, but it's never going to be exactly 0. Okay, and there's many places it's very prevalent, this softmax transformation everywhere. We can use it both as a loss function. For example, if you use a softmax in the output and then use a cross entropy loss. But you can also use it as an attention mechanism, as something which is a hidden layer inside the neural network. Another case which is very familiar, even maybe more familiar than softmax, is argmax. So in this case, we take the same vector Z, but we don't want to get the probability distribution in the end. We just want to have all the probability mass in a single event, which is the one that corresponds to the largest component of Z. Okay, so this is going to return a one-hot vector. Pointing to the highest scored index of Z. There's 2 ways in which we can think of this. We can either think of this as a limit case of softmax with the near 0 temperature. So if we take our original vector Z, we divide it by a very small constant, we make that constant approach 0, and we apply the softmax transformation, then our distribution is going to get peakier, very peaky. And in the limit, it's going to be exactly a one-hot vector. So I'll call this the temperature trick, and it's widely used in many different places. Another way of looking at argmax is as the solution of a linear program. Okay, so if we are maximizing a linear objective, Z transpose P is our variable, and P is constrained to be in the simplex, then the solution of this optimization problem is going to put all the probability mass into the largest component of Z. This is the thing that is going to maximize the linear objective, okay? And so this is a way of expressing this as a continuous optimization problem, a linear program. but where the solution is still going to be a one-hot vector. I'm putting this in this form because I'm going to bring this up in a bit. Okay, so if you want to look at this schematically, for a concrete case, like Z is here a vector of 5 dimensions. Some of these, some components of Z are positive, others are negative. Softmax would map things to a probability vector represented here, where the sum of these blue bars is going to be 1. But you can see that there is probability mass for all the labels, all the 5 labels. Whereas argmax is going to put all the probability mass in the largest component of Z, which happens to be the first index. So we can think of argmax as a very extreme case of sparsity, but it turns out that this transformation is discontinuous. Okay, so if I do a small perturbation on the components of Z, this bar is not going to move. We are going to get exactly the same outputs. And if we do a perturbation that is big enough, then we can have a sudden jump where suddenly the largest component of Z is something else, and this bar is just suddenly jumping to some different level. And so one question that we ask here is if there is something which is at the same time sparse and differentiable. And the answer to this question is yes. There is this transformation that we have been studying for a long time called sparsemax, which is able to do something in the middle, in between softmax and argmax. Okay, so for this same Z, sparsemax would put a probability mass on 2 labels, and all the other labels will get 0 probability. And now if we perturb Z a little bit, these 2 pink bars are going to move a little, but they're not going to jump. Okay, so it's possible to do end-to-end to do gradient backpropagation with a transformation like this in the middle. So how do you define sparsemax? Actually, the definition is very simple. We just define it as the Euclidean projection of our vector Z onto the probability simplex. Okay, so we are looking for the point P that is the closest in terms of Euclidean distance to our original vector Z. Okay, so this can be represented as this quadratic problem. Okay, we are minimizing the squared L2 norm of P minus Z subject to P being in the simplex. Expanding the square, we can also write it in this way. Okay, so we can write it as maximizing a linear function Z transpose P, but with a quadratic regularizer, where we are using the L2 norm, the squared L2 norm of P, as a regularizer. Okay, and the reason why I chose this formulation here is that if I go back a little bit, when I talked about argmax, I was expressing argmax this way. Okay, so this is, we can regard this as an unregularized problem, right? It's exactly the same as this, but without this thing in red, without the regularizer. So we can regard sparsemax as a regularized version of argmax, if you want. And sparsemax actually, has several very nice properties. So one of them is that it's sparse, and this is where the name comes from. So these Euclidean projections onto the simplex, they have a tendency to hit the boundary of the simplex. The boundary here means that it can be like a vertex or a line connecting 2 vertices, or basically something that assigns 0 probability to several labels. Okay, those points that are in the boundary of the simplex are the points that correspond to vectors P, which have lots of zeros. And so in that case, we get sparsity, right? So sparsemax is able to give us a sparse P, unlike softmax, where P was always dense. And another thing that is a very interesting property is that even though we defined it in this variational form as a solution of a minimization problem, it turns out that this transformation is piecewise differentiable. So it's differentiable almost everywhere, which means that we can actually do gradient backpropagation with this. Computationally, it's also something efficient to compute. So we can solve this problem in linear time, linear with respect to the dimension of the vector Z. It's not as fast as softmax, but it's not much slower with a carefully done implementation. And last time we benchmarked it, it was like a less than 1.5 times as slow, so not terribly slow. And the backpropagation can actually be done faster because the gradients, only the gradients that correspond, only the gradients with respect to the components of P that are not zeroed out need to be computed. So the back propagation is sublinear. So here are some examples in 2 dimensions. So in 2 dimensions, softmax is the sigmoid, the logistic function, and sparse-max corresponds to a hard sigmoid, right? So everything is piecewise linear, and you can see that asymptotically they are similar, but sparse-max has this exact saturation. And the same thing happens in 3 dimensions. Okay, so in 3 dimensions, again, the asymptotics are similar, but sparse-max has this piecewise linear shape, and it has this exact saturation. Okay, so by the way, feel free to interrupt me with questions if there is any question. All right, I'm just keep going. Okay, so so something that Vlad Nikolai, I don't know if he's attending this talk, but he has done lots of work on this, and Mathieu Blondel developed was a generalization of sparse-max for arbitrary regularizers. So we talked before about L2 regularizer, which gives us sparse-max, but it's possible to take any convex function omega and define a generalization of argmax, which uses omega as a regularizer. And it's also possible to, for particular choices of omega, to recover things that we already know. So of course, with omega equals 0, we get argmax. We have seen that already. With omega equals, with omega, the L2 regularizer, we get sparse-max. We also saw that. But it turns out that if we choose omega as the negative Shannon entropy, then we recover softmax. Okay, so this is interesting because it shows that softmax can also be regarded as a regularization of argmax with just a different regularizer and a very natural one. But still, this begs the question of maybe you can generalize this even further, or have like a family that generalizes all these 3. And the answer again is yes. So this happens if we pick a regularizer called the Tallis entropy. This is a generalization of Shannon entropy. There is a very beautiful theory, motivated in statistical physics that explains why these entropies are interesting. I'm not going to get into the details here, but they are defined as a continuous family of entropies parameterized by parameter alpha, scalar, which is positive or non-negative. And that includes, as a particular case, when alpha is 1, we recover in the limits of the first expression, we recover the second expression, which is a negative Shannon entropy. So this really generalizes entropy. And now picking particular values of alpha, we recover the 3 cases that we just saw. So if alpha is infinity, we get argmax. When alpha is 1, we get softmax. When alpha is 2, we get sparse-max. There's also other interesting things that we can obtain for other values of alpha. There's also a very nice properties of these kind of transformations. So for any choice of alpha which is strictly greater than 1, basically anything which is just a little bit beyond softmax, there is a propensity for sparsity. Okay, so we can obtain transformations that are sparse. Moreover, this sparsity increases with alpha. So the larger we make alpha, the larger we have a propensity for these transformations to be sparse. So this is another way of controlling pickiness, and in this case, sparsity, which is an alternative to using a temperature parameter, which is the typical tool that is used to make distributions pickier. And for any choice of alpha, we can it's possible to do the forward pass efficiently using a bisection algorithm, and the backward pass in all cases can be run in sublinear time. So this is a picture that shows different values of alpha for the 2D case. Again, for alpha equals 1, we have softmax, so we have this logistic function. For alpha equals 2, you have sparse-max, so we have this hard sigmoid in green, and we have a lot of other things in between. The value 1.5 is particularly interesting. It's really a sweet spot. It has a bunch of interesting properties. One of them is that, so this corresponds to the dashed black line here. One property is that this function is differentiable. So it's sparse and differentiable. Okay, so so for these points where it becomes 0, the derivative here exists. Okay, so it matches. It's different from sparse max in that sense. Another interesting property of 1.5 is that there is an efficient exact algorithm to compute the transformation that Vlad Nicolai derived. Lots of math involved, but it's nearly as fast as softmax, so it's more efficient than other values of alpha, apart from 1 and 2. And if you want to play with this transformation, it's very easy to do. There is this entmax package. I think you just need to pip install entmax, and the things are very easy to use. Every instance of softmax you can easily replace by entmax and see what happens. This is particularly convenient if you are working in a problem where you believe that sparsity might be important. For example, if you want to select things, if you are computing probabilities of a large set of labels and you believe that some of them are completely irrelevant. Okay, so here we are putting 1.5 entmax, alpha 1.5 in the middle of the plot. We can see that it's a little bit less sparse than sparse-max for the same z, but it's still sparse. Okay, so the second label is also gets a probability of 0, and all these transformations are, except argmax, are smooth. Okay, so if you perturb z a little bit, these bars are going to move a little bit. Okay, so we apply these in many different problems. Machine translation was one of them, and generally sequence-to-sequence models. This is work of my student Ben Peters. He kept doing this after this paper. Applying this to morphological inflection, grapheme to phoneme, and a bunch of other tasks. The first thing that we tried to do was to replace the classical softmax Badanao attention by sparse-max attention, by using sparse-max in the attention mechanism. And what happens is that we get like a sparse set of alignments. Okay, so many alignments between many words are going to be exactly 0. Okay, so this gets a little bit closer to the classical notion of alignments that people used in statistical machine translation. We argue that by looking at these alignments, you might understand better the failure modes of the models, and you can try to interpret things somehow. I don't want to go into this territory about attention being interpretable or not. There's lots of debate on that, but I think there's still very interesting things that we can do with attention. This has also been extended by in another paper. Well, one of the authors is Pedro Ferreira. I don't know if he's here, but I know that he's a PhD student now in Amsterdam, where we also put an upper bound on how much attention a word can receive, which allows us to model things like fertility, which was it was a very important concept in IBM models in statistical MT. It's also possible to learn alpha. This is the work of another student, Gonçalo, with this paper at MLP, where basically they took a transformer architecture. And as you know, transformers have many self-attention layers, many attention heads, around in the simplest architectures, they have around 200 attention heads. And what we wanted to do here is to learn a specific alpha for each of these attention heads. Because we observed that some attention heads they prefer to be more sparse, while others prefer to be more dense. There's several other work from done in other groups, for example, in Ivan's group by Elena Vojta and others, that try to understand better what is being captured in these different attention heads. And this idea of learning alpha captures that in a way that is end-to-end differentiable, because you can also differentiate these alpha-entmax transformations with respect to alpha. So another take on interpretability and explainability in that case is the work of Marcos Treviso that he presented in the black box NLP workshop, where we try to formulate the problem of explainability as follows. So we have some classifier. The classifier is outputting some prediction. Let's call it y hats. And then we have an explainer. The explainer can be either something separate, if you do post-hoc explanation, or it can be something internal in the classifier. But so there is some explanation mechanism which is going to produce an explanation for this label y hats. Okay, and we are going to model this explanation as a message. Okay, and the way we model this, it's very flexible. But if you want to think about a concrete case, you might think that the problem is something like document classification. Y hat is a label for the document, for example, a sentiment label, positive or negative. And this message is basically highlighting the words that indicates that justify this label. And then there is another component. We call it a layperson. It can be a machine or it can be a person. And the layperson receives the message. It doesn't look at the prediction of the classifier, and based on the message, tries to guess what the label was. And its guess is going to be Y tilde. And you can measure the success of this process by counting how often Y tilde agrees with Y hat. So the goal is not for the layperson to identify the correct label. The goal is for the layperson to match the label of the original classifier, even if it's wrong, based on the information that is in the message. So it's a very simple way of formulating simulability, also called forward simulation prediction, where we want to check if there is enough information in the explanation that allows recovering the original prediction. Okay, so this is not a perfect setup for explainability, but I think it's a crucial element. So in this paper, we also put together a bunch of different ways in which we can relate methods for feature selection to several techniques for explaining predictions. So if you think about classical feature selection, usually the idea is that you want to interpret the model. Okay, so you want to select features statically from the model. Some features we believe that are going to be relevant no matter what the input is. And there's many different techniques. There's a taxonomy of methods, which includes wrappers, filters, embedded methods, and so on. All these methods are about selecting features statically in the model. And I'm arguing here that we can draw a parallel between each of these kinds of methods and methods that are used today for prediction explainability. So for example, if you think about, let's say, erasure or leave one out, this works by repeatedly removing or adding, depending, there's several variants, removing one feature, feature from the model and see if the prediction is going to change when that feature is removed. And this is not very different from what wrappers do, for example, with forward selection or backward elimination. And the same thing happens with other methods that can be regarded as filters. And maybe the most obvious connection is with embedded methods. So in the feature selection world, we have methods like L1 regularization. In prediction explainability, we have things like sparse attention, which is what I'm going to talk about. Okay, so there's also a bunch of different ways in which these things have been extended. I think I might be moving too slow. I will speed up a little bit. So we have extended these in different directions, putting constraints. I think I already mentioned some of these. There's very nice work done by Vlad Nicolai and Mathieu Blondel on fused max, basically the counterpart in these transformations of fused lasso that is able to promote structured sparsity. More recently, there is this work where we generalize this to structure prediction using these transformations called SparseMap and LP SparseMap, which I think are really, really cool. And a very nice way of dealing with constraints. So if you are working on a problem for which we want some latent variables and you want to inject some logical constraints to put some structural bias when learning your model, you can define a factor graph. In this factor graph, you can put a bunch of constraints, logic constraints, budget constraints, whatever you want. And then you can learn everything end to end. And with LP SparseMap, you can use this as a differentiable layer. So you can differentiate through this factor graph. We have applied this, for example, to generate structured explanations in a work that my other student, Nuno Guerreiro, presented in MMLP. All right. So we also generalize this to continuous attention over continuous sets. So far, I only mentioned attention over a finite set, for example, a set of words or a set of pixels in an image. But it's possible to generalize this for attention densities over a continuous set. I'm not going to get into details, but we use this, for example, for VQA, when we want to answer a question that relates to something in an image. And we could select like a continuous region of an image, for example, an ellipse, that contains a justification to the answer. And the usual operations are still tractable to do with if you make certain choices to parameterize these continuous distributions. Okay, so I think I'm going to let's see. So I have 8 minutes, right? So I think I'm going to skip this second part and maybe jump to the mixed distributions parts.
I think you have 5 more than what you said, I would say. Yeah.
Okay.
I started 5 minutes later. Yeah.
Okay. So okay, I'll still skip some slides, but I'm going to jump to the interesting part. Okay, so actually, I think I need the motivation first. So we also use these transformations as the output layer, not just as an attention mechanism. But if you want to do that, there is a challenge that we get, which is if we get a probability of 0 to a gold event, to something that really occurs in the data, then log likelihood is going to be -infinity, right? So we cannot use this out of the box. Instead, what we propose is to use something called Fenchel-Young losses, which is a family of losses with very nice properties. Okay, so I'm going to skip this part and jump to the Fenchel-Young losses. Okay, so recall that when we talked about regularizing the argmax transformation, we talked about having a regularizer, a convex regularizer omega, and we saw that for different choices of omega, we recover some familiar transformations, right? Now, you can also use this omega to define a loss function by taking the convex conjugate of this omega. I'm calling it omega star. This convex conjugate is, this is a very crucial concept in convex optimization. It's kind of a dual function of our original omega, and it's now going to be a function of z, a function of the scores, and not a function of the probability distribution. It's defined this way. Okay, so it's a linear, it's a maximization over the simplex of a linear term minus omega of p, based on omega and omega star, we can form a loss function that I'm calling here L omega that tries to kind of calibrate the score z and some ground truth vector q. So I'm assuming here that q is a vector in the simplex. It could be a one-not vector. This is what typically happens if you do if you're doing classification. But so we can define this loss function. And those of you who are familiar with convex duality might notice that this is very similar to something called the Fenchel-Young inequality, which basically states that this quantity for any convex omega is going to be non-negative, okay? Which is a property that we usually want to have in loss functions, right? We want loss functions to be non-negative and to be non-negative and zero, if and only if there is kind of a perfect calibration between the model and the label that we are observing. And this is exactly what we get. So these loss functions for any choice of omega that is convex, they are always non-negative and they are zero if and only if q, so the ground truth distribution, is the regularized argmax when z is given as input. Okay, so for example, if this transformation is sparsemax, this is going to be zero if and only if q is exactly the sparsemax transformation of z. Apart from that, these losses are all convex and differentiable. Convex with respect to z, and they are going to be differentiable, and the derivative, the gradient, can be written this way as a difference of these two terms. One term that applies this argmax transformation to z, and another term that is the ground truth label. Okay, and if you recall the gradient of the cross entropy loss, you might see that it's very similar. In cross entropy, the gradient of the cross entropy loss is the difference between softmax of C and Q. So this immediately generalizes the gradients to other transformations besides softmax. So there's also an interesting relation with Bregman divergences, but I need to move on. So I'm good. I just can't resist showing this. So these losses have a very nice property, which is they, for if you pick these Tsallis entropy as the regularizers for any alpha greater than 1, we already saw that the transformations that we get are sparse, But if you look at the loss functions, it turns out that they all have margins. Okay, so there is this a very nice tight connection between a transformation being sparse, the corresponding loss having margins as in the hinge loss of SVMs, and the entropy of having a certain property. So in fact, you can relate the margin size with derivatives of the entropy on on 0 and 1. So I'm skipping details, but in this JMLR paper we study this in more detail, and I find this a very fascinating property. I think we never managed to exploit this in practice that much, but it's a very interesting property. All right, so just mentioning a few ways in which we use these losses. We found them very useful for sequence-to-sequence tasks. So for example, if we use these losses to decode during generation, for example, for machine translation, if for this example, we have a German sentence like this, and when the model starts to generate English, it only assigns non-zero probability to these 4 words in English. Everything else gets 0 probability. And sometimes the model is very confident. So for example, here is another. The model assigns probability of 1 to is and probability of 1 to another, which means that you can auto-complete, okay? And this is something which is useful to use in a scenario, for example, of predictive translation, where a user either chooses an option in this drop-down list, or it replaces it by something else, or just presses a key to accept the suggestion. We also use this for generation, where we use ntmax for sampling as opposed to decoding. And now I'm going to jump to mixed distributions in the remaining 5 minutes that I have, something around that. So, so the idea is, how can we use sparsity to bridge the gap between discrete and continuous? And if you remember, this was the problem that I used to motivate this. So we have John who's commuting between work and home. If you want to model the position of John, we'd better use something which is hybrid, neither completely discrete or completely continuous. But actually, it's a very boring life just to commuting between work and home. So let's try to make this more interesting. Let's suppose that there is also a pub, and John sometimes spends a couple of hours in the pub. Okay, so now he needs to go from home to work, from work to the pub, and back from the pub to home. Okay, and you need to account for his position in all these different circumstances. It could be either with some probability mass in these exact vertices, or it could be walking from one place to the other, or sometimes there is some happy hour in the pub and he might get a more erratic trajectory back home. Okay, so it can also be in the interior of this triangle here. So in theory, it can have some density that takes this entire simplex. Okay, so we need a way, if you want to model a problem like this, you need a way to represent this probability mass in all these different parts of the simplex, and not just the vertices, edges, or face. Okay, and in our recent ICAI paper, we developed a framework to do this. So let's first think about the simplex. So I'm denoting here by Ri the relative interior of the simplex, densities on there's lots of work developing densities on the simplex. The common densities that people use are the Dirichlet distribution, also the logistic normal, and more recently the concrete distribution, which is a way to relax a categorical distribution. Okay, but all these densities, they never place any probability mass on the boundary. Okay, so they could not model this problem with John. So this is what the Dirichlet is doing. Different choices of concentration parameters linked to different shapes of the distribution, but you're never going to get probability mass in the boundary. With the logistic normal, we can measure model some correlations between these different dimensions, but again, you don't get any probability mass in the boundary of the simplex. With the concrete distribution, this is good to relax the categorical, but again, we never get a probability mass in the boundaries. I mean, you can get closer and closer to extreme points, but it's not that we want here. On the other hand, people have developed a few strategies to deal with the univariate random variables. So when k is 2, you can think of the simplex just as a line connecting 0 and 1, where the probability, we have probabilities p and 1 minus p, and p is in this interval. And then people have worked with truncated densities. two of them that are that have been used a lot are the hard concrete. I think this has been developed here in Amsterdam by Luiz et al., where the idea is to take the concrete distribution, stretching it, and then applying a hard sigmoid transformation. And this way, you get point masses at 0 and 1 due to this transformation. It's similar to spike and slab, which is a technique related to this thing that I'm describing. Another thing that has been done is to start with the Gaussian and then truncating the Gaussian. So it's basically the same thing, but instead of stretching, the Gaussian is already, it's over the entire real line. So you can just truncate the Gaussian and have point masses on 0 and 1. Okay. The problem is that it's not straightforward to generalize these techniques to k larger than 2. Because if you are just with the k equals 2, you can have these Diracs for the points 0 and 1. But if you are with a higher dimensionality simplex, then it's not. We will need to have Diracs of several orders, and it's very hard also to work with entropy in these models because the Dirac deltas have minus infinity differential entropy. So what we propose here is to start with our simplex and then think about the phase lattice of the simplex. Okay, so we are going to look at how these different phases of the simplex relate to each other. And by phases, I mean things that includes the vertices, so the 3 corners of the simplex, also the lines that connect these vertices, and also the interior of the simplex. Of course, with larger k, you get a lot more phases. Okay, and the problem with the so what you need to solve is if you want to model, if you want to have some probability mass in these different phases, we need to be able to define a base measure in order to define those probability distributions on top. Okay. The challenge with that is that the typical thing that people do is to start with the Lebesgue measure, with some fixed dimension. But everything which is not the interior of the simplex is going to have a measure 0. So you need to do something different. And our solution for that is to have like something that we call a direct sum measure that assigns a mixture of different Lebesgue measures on every phase. So we are going to pick the right dimensionality for each phase, and then the measure of a subset, which can be distributed across several phases. It's going to be a sum of the measures on each phase. Okay, so this is it's a valid measure. It satisfies all the axioms that we need, and we can regard random variables using these base measure that we call mixed random variables as a generalization of both discrete random variables. Those are the ones that only assign probability to 0 phases. 0 phases are the vertices of the simplex. And also generalization of continuous random variables that only assign probability to the relative interior of the simplex. So mixed random variables, in contrast, they can assign probability mass to everything. Okay, so to define a mixed random variable, you need to specify the probability mass function of over the phases. And we need to specify, given a phase, what is the conditional density on that phase. Okay, so we need these 2 distributions here. Once we specify these, then we can specify the probability of sets by considering a mixture of distributions on the phases. So I think this is easier understood with an example. There's 2 ways that we can use to characterize mixed random variables. One is an extrinsic characterization, where we start with a distribution over the ambient space, in this case, the k-dimensional Euclidean space. And then you apply a projection or any transformation that maps these points to the simplex. Another way is to use an intrinsic characterization where we specify these distributions, the probability of phases and the conditional probability within each phase directly on the simplex. Okay, so the extrinsic ones are a lot easier to define and to work with, and we tried 2 of them. So one was inspired by the hard concretes that we saw before in 2 dimensions, but now we can generalize it to more than 2 dimensions, where we first sample y prime from a concrete distribution. Okay, then we need to stretch this distribution by multiplying by coefficient tau, And then after stretching, we apply the sparse-max transformation. Okay, so because the sparse-max transformation is going to move us to the simplex, but where we can have some sparse components, then y can be in any phase of the simplex. And interestingly, if we just do this, exactly this with k equals 2, we recover the binary hard concrete. Okay, so this is a generalization of the Luizos et al. Construction. Another possibility is to use a Gaussian as a starting point as opposed to a concrete, and then projecting a sample from a sample of a Gaussian from with sparse-max. So this is what we call a Gaussian sparse-max. And we can regard it as a sparse-max counterpart of the logistic normal. In the logistic normal, what we do is we sample from a Gaussian, and then we do the softmax of that to obtain a point in the interior of the simplex. But this is now something that can assign probability mass to all phases. So here's a comparison between the logistic normal. This is the level curves of a logistic normal. And here is the Gaussian sparse-max, which can assign probability mass, for example, to this edge. Okay, so we also, I think I'm out of time, so I think I'm going to wrap things up. We can also define a distribution called the mixed Dirichlet, which is an intrinsic characterization. Here we define things directly on the faces of the simplex. We do some smart parameter sharing to make sure that we don't blow up the number of parameters, and then we mask our Dirichlet to be able to define a conditional distribution of y given the face. And all the operations that interpret perform here can be done efficiently with dynamic programming. So sampling the phase is something that can be done with dynamic programming. Okay, so I think I'm going to skip this, but we built some information theoretic concepts on top of these mixed random variables. There is a way of defining entropy which generalizes discrete entropy and differential entropy. I find this very interesting. For example, one of our findings is that the maximum entropy distribution is not going to be log of k, which is what happens in the discrete case. So if you have a random variable with k possible values, the maximum entropy distribution is a uniform distribution over these k possible outcomes. It's log of k. But if you are now allowing for this mixed space, then the entropy needs to be a bit higher, because if you assume that you are working with a categorical, it means that you already know we are already constraining the faces where the outcomes of your where a random variable is. Okay, you are always only looking at the vertices. But if you allow your variable to be a sparse variable in the simplex, then the entropy has to be higher because you have higher uncertainty, and you have a closed form expression for the maximum entropy in those cases, which relates to something called Laguerre polynomials. It's also possible to define KL divergence, mutual information, and all those things. And we did several experiments. I am not talking much about experiments in this talk, but one experiment that we did just to validate this idea was in the communication game. It's a very simple toy problem. We assume that there is a communication between two agents, where the first agent sees some image, and then it needs to communicate the code to the second agent that represents that image. And the code here is just a single symbol. Okay, and then the second agent he sees 16 images. One of them is the right one, and there are 15 other distractors. And the idea is that the second agent needs to use the code provided by the first agent to identify which is the correct image. So if he just random guesses, he gets a very low accuracy of 6.25%. So we compared different methods to do this, including classical ones like Gumbel softmax, straight through with Gumbel softmax, and so on. And you looked at the success rate of communication in those cases, and also at how many non-zeros are produced in the code that is being transmitted. So we use a vocabulary of 256. Okay, so Gumbel softmax is completely dense, so it always gets 256 non-zeros. Straight through is completely sparse, so it gets just one non-zero. And we see that with Gaussian sparse-max, we get a lot. You get a mix. Things are very sparse. We got on average 1.57 non-zeros, and we have a very high success rate. With the hard concrete, we don't get as much sparsity, but it's still much sparser than Gumbel softmax. And and the success rate is also high. Not as good as Gaussian sparsemax though. There's a few other experiments in this paper in other settings, but I think I should conclude. So today I talked about transformations from real numbers to distributions. These kind of transformations are very ubiquitous. We introduced new transformations to handle sparsity, constraints, and structure. They are all differentiable. We can use them either as hidden layers or output layers. And in the end, I talked a little bit about mixed distributions, and I argued that this could be an interesting thing to do to bridge the gap between the discrete and continuous worlds. So thank you very much. And if there is time for questions, I can take some questions.
Thank you, Andrea. There is some time for questions. Let me see here. My question window jumped around. If you have a question in the audience, you can perhaps now typing in the Q&A tool is not the most efficient way. You could also just speak up. Yes, please. I see a hand. Ivan, we can't hear you.
Oh, can you hear me now?
We can hear you. Yes.
Yeah, thank you for very interesting talk. So I had a question about the communication game, because one of the things in this community people look into is what kind of protocol is induced, right? About the properties of protocol, how, for example, compositional it is, and conditionality in some way, a measure of how systematic mapping from semantics of what you want to transmit, right, to the protocol. Do you think using sparse max or maybe sparse Gaussian, and I forgot the terminology you use, can help in getting more structured, more compositional communication? Mm-hmm.
This is a very good question. So in this work, we just communicated a single symbol. Okay, so we didn't expect to have any interesting regarding compositionality and things like that. But I think that people that work in this space, I think argue that you need some kind of bottleneck for something interesting to emerge. And I see a few avenues of extending our approach to do that. One is to do something with sparse map, where we put some structure, and then we can define whatever structural bias you want to impose, hoping that this will lead to something interesting in the end. Or we can try to study what happens if you have a string of symbols as opposed to a single symbol. And we didn't do any experiments on that yet, but it's possible to derive some interesting properties of sequence of mixed symbols. For example, you can define something called a mixed language, a mixed regular language, and having like a machine that generalizes some properties of FSAs and so on, and operates over these sparse sets of symbols. So I think this might be a potential direction of future work that could maybe target some of the problems that you are asking.
Mm-hmm. Yeah, that's super interesting. Yeah, thank you.
There are a few more questions, but I guess we'll close here. Maybe we can thank once again our speaker. Thanks, Andrea.
Thank you.
I think let me stop the recording.